Okay, good afternoon everyone. So let's continue our class. So today we're gonna do one exercise on a mass spring damper system, and there are 4 questions here. Number 1, you are asked to find transfer function using conventional method, and then you find the transfer function again but using a state space representation. Number 3, using MATLAB or SciLab, find the discrete state space representation of the system if all the coefficients k and b equal to 1. And the last question, you will need to simulate the system using MATLAB or SciLab. So I think the first 2 questions are very easy, so you can try by yourself first. Okay, so let's do it now. I can give you some hint. So you apply Newton's second law to a free body diagram. So first you make a free body diagram, and then you substitute the force element by force. So here for the spring, the force generated from spring K times X, and force generated by damper B times H dot, and you have the input force F of t. Okay, so you apply Newton's second law here. Sum of all external force on mass equal to mass times acceleration. Okay. Okay. So from this equation, we can substitute all the force element in here into this equation. So some of you already got the right equation. Now I can write for the rest of you. So here all the force, external force, are BH dot, KH and F. So because the direction of KH and BH dot on the opposite direction of H, then we use minus KH minus BH dot plus F of t equal to MH double dot. So we have MH double dot plus BH dot plus KH equal to F of t. Then we can easily apply Laplace transform to this equation. Then we can get ms square h of s plus bs h of s plus k h of s equal to f of s. Then the ratio between output h of s and f of s equal to, this is transfer function, equal to 1 over ms square plus bs plus k. So next for question number 2, you need to transform this equation, the ordinary differential equation, into state space. So mh double dot plus bh dot plus kh equal to f of h f of t. Okay, so I give a hint. Let h1 equal to h itself and h2 equal to h dot. So you need to write down the equation h1 dot equal to what, and then h2 dot equal to what. Okay, so finally you can have the state equation h1 dot h2 dot equal to coefficient here h1 h2 plus you have coefficient here and times f of t, which is the input. So you have here as h dot, so it means let h equal to h1 h2 like this. Okay, so you have h dot equal to ah plus capital H plus b u, where u equal to f of t. Okay, so you will need to fill out what is the coefficient a and b. So once you have a state space representation for continuous system, then you can use Laplace transform. Then you have s h capital H of s equal to a capital H of s plus b capital U of s. Then you move a h of s to the left hand side. You can have s h of s minus a h of s equal to b u of s. So here you have hs. You can take hs as a factor. So here a is matrix, you can get matrix here, but here s is scalar. If you have scalar, let's say you just use s here. Now you have scalar minus a matrix. That's not right. So you need to have identity matrix. This identity matrix times hs is still hs same. You will get the same here. Then you get b u of s here. So then you find the ratio. So transfer function equal to the ratio of h of s over u of s equal to si minus a inverse times b. Okay. Where oh sorry, because h here is, I think, yeah, h here is state that we have h1 and h2. Actually we should introduce output equation, right? Output equation y equal to what? Because h here we have h1 and h2. Suppose you only measure the displacement h. If you want to compare with this method, h here represent only the displacement h, right? Here h. But if you want to when you transform into state space, h here represent h1 which is displacement and h2 which is velocity. So you have two variables here. Let's say now you want to compare with the conventional method. You choose output as h only, which is h1, right? So if it only h1, it means you have 1 0 times h1 h2. Okay, where you call this matrix C. So the transfer function from input to output. So this one just from input to states. Okay, so I don't call this a transfer function. Then transfer function from input to output. Input u well, or f of t to output y of t is defined by y of s, which is equal to c times h of s. Then so actually from this equation you don't need to write the ratio like this. We just need h of s like this, and then you just keep u of s here first. Okay, so here you can have c times h of s from this equation. So you substitute h of s, you have c s I minus a inverse times b and times u of s. Because you have single input, single output, then you can write transfer function equal to y of s over u of s equal to c s I minus a inverse b. So now let's finish up here what is a and what is b, because h1 dot t equal to h2 and h2 dot equal to minus k h1 minus b h2 over right, and minus plus 1 over times u. So in here we have 0 1 and minus k over minus b over okay, and here we have 0 and 1 over okay. Then we can substitute a, b, c in here to have transfer function, right? So you can have 1 0 here times s times I, you have s 0 0 s minus a here is 0 1 minus k over minus b over and all here inverse, and then time b 0 1 over okay. So on here you need to simplify the inside the big parenthesis. You have s minus 1, you have k over m, and you have s plus b over m, and all inverse, right? Okay, so you need to find the inverse. What is the formulation of the inverse? Let me just find this inverse first. This one equal to what? Equal to 1 over determinant. Let's call this is matrix M. So determinant of 1 over determinant of M times its cofactor transpose, right? Cofactor transpose. Cofactor mean here you have s plus b over m, and here you have minus k over m, and here you have 1, here you have s, and you transpose. Okay, equal to what? Determinant. Determinant is s square plus b over s, right? And plus k over m. Okay, how about this? You transpose it. You have, when you transpose it, you have s plus b over m, you have minus k over m, you have 1, and you have s. Okay, so now TF equal to just let me write down determinant here for short notation, and then you have C 1 0. Oh, now I use red here. I want to use the color red. So now you have, or you can have a transfer function equal to, just keep a 1 over determinant here, and then you have C0 as a 1 0, and you have your new matrix here, s plus b over m, and am I correct? When I transpose, yep, cofactor transpose. Yeah, I think this is correct. Here minus k over m, here is 1 s, and here you have 0 1 over m. Okay, so now when you multiply this, you multiply 1 0 into this, you only have what? only the first row, right? And so you have the first row. When the first row time this one, you only have this one time this one, because this one is 0. So actually you just have 1 over and this one determinant of So finally transfer function is just the same as before. No, not this. Equal to, rewrite this one. So here you just have s square plus bs plus k, just same as before. So here I just try to illustrate for you that even though we use different method, because you just have a mass spring damper system, then you want to find transfer function from input to output. Okay, input as a force, output as a displacement h. Then of course you have just this one, just this transfer function. Right, so it's same as before here. Right, because 1 over here you just get 1 over and all here here you can move it to the denominator and can cancel all this Okay, maybe I should oh, this is bad. I can write in detail a little bit, just like this. TF equal to 1 over s square plus b over s plus k over and then just move to denominator. Okay, now let's look at question number 3. Using MATLAB or Scilab, find the discrete state space representation of the system if k and b are equal to 1. So what you have in the state equation, okay, is like this. So you have continuous state space representation as capital H dot equal to 0, 1 minus k over minus b over times H1 H2 plus 0, 1 over times u. Now you discretize, the system, transform it into discrete system. So in the formulation you learned before, from the formulation you learned before, so now b and all parameter equal to 1, I should write down like this: 0, 1, minus 1, minus 1. yeah, maybe just capital H plus 0 1 U.
Why is it 0 1 and 0 over n for the
Which one?
yeah, this one?
Why?
Why does it why do we transform the other n into just one?
Oh, because here we choose all parameter equal to 1.
Okay.
Yeah. Now you can use MATLAB or Scilab to find a discrete system. So this one is F, this one is G, right? Yeah. If you still remember the lecture, how do we find the discrete system? So we need to find phi, phi and gamma, right? So actually phi and gamma has formulation to be like this. This is phi and this is gamma, but it's not easy, right? Because this is exponential, and if you expand Taylor series, you need to do a lot of multiplication, right? So you need to use software to compute for you. So what you can do first, define state space for linear system. So here is the instruction. First you need to find, for Scilab you need to use system linear and using ABCD. So ABCD, so okay, our system is H dot equal to AH plus BU, and then Y equal to CH plus DU. So you already have know A. Yeah, I just call it F before, but actually it's saved as A, right? Okay, here A, B, C, D. So C is 1, 0. D is just 0. Okay. So let's try. Okay, I think I can write down for you A, B, C, D here. A equal to 0, 1, minus 1, minus 1. B equal to 0, 1. Okay. C equal to 1, 0. And D equal to 0. So in Scilab you use system linear. Okay, define your system equal to system linear like this, and then you input A, B, C, D. So here is the instruction of using system linear. You define system SL as a system linear, and then you put the domain. Domain here means the discrete or continuous. So first you define it as a continuous here, okay, and then you put A, B, C, D in there. After that you can transform it into discrete. Alright, okay, so let's try. Why? Something wrong with this. Okay, so here you just use domain continuous, and then you put the input argument A, B, C. Also D is now it's optional because D is 0, right? So that is okay whether you use it or not. After then, here you can use this function to transform it, okay, from linear to discrete. This is system linear, discrete. This one system linear but continuous. And here is the sample time. So in the problem I should give you the sample time as well actually. So let me give the sample time and the sampling time. T equal to, just say 0.01 seconds. Okay. So now try to use this. This one. You already have the continuous state space system. Then you use this function to transform into discrete. So actually you can use, just call it system discrete equal to, maybe I call this one a systems continuous. Oh, okay, just do like this here, or, and then equal to discrete, and you have system continuous here, and then you use sample time 0.01 like this. Okay, so we just learned that there is a error on the instruction from DCLab help. If we don't use input noise then there is no output covariance of the output R. So what we need to do is to erase this term. We don't have something to return for R. So here just system discrete. Yeah, this is the correct way to use transformation from continuous state space to discrete state space. So then let me do it in DCLab. Okay, open new DCLab node. New. So first define a equal to 1 0 minus 1 minus 1, and then b equal to 0 1, and then c equal to 1 0, and then d equal to 0. Sampling time equal to 0.01, and then let's define system. This is for continuous system linear of in continuous domain, and then input argument A, B, C, D. After then we transform it into discrete using so system discrete equal to let me check again, what is it, discrete. So DSCR of system, and then sample time, sampling time. So I wanted to print out the system discrete. So side note I should use so 2, transform continuous to discrete, C to D. Then I run it. System D. So it seems we have the system in the discrete time domain. So then we can continue to question number 4. Here, simulate the system using MATLAB or Scilab if the input f is a unit step function. Then here we need to define input u as unit step. So how you find unit step? Just one. So how many points you want to compute? Let's say 1 row and 200 points. And then so the time should be 0 up to length of u, from 0 up to length of u, so should be how many points? Should be 201 points, right? But I only need 200 points, so I use like this, and then multiply it by sample time. Multiply it by sample time. This is just time, and the most important thing is to simulate. You use this sim, right? Let me show the previous result here. This sim, input as a system and input, right? The input argument. So just call it output y equal to dsim simulation of system discrete here, and then the input u. Okay, finally you can plot t versus y. This is not correct. A1 0 minus 1 minus 1 0 1. Oh, 0 1, not 1 0. 0 1. So again, yes, 200 point. Then we only see the beginning of transient. So perhaps we need to generate up to 2000. Okay, 2000 point. Okay, so this is the result of the simulation of discrete system. Okay, so let's do the next exercise. In this exercise, you are given a state space model of kinematic of lateral motion of a car, where h1 is lateral motion and input u is steering angle. Okay, so when this car has a velocity, the linear velocity v, and then if you steer the angle, for example, to the left, then it has a motion to the left. Okay, and if you steer back, then it may keep the portion of the lateral at a constant, something like that. Okay, so in here you will need to transform the continuous state space into discrete. For the number 1, you find transfer function just to warm up, and then you use software MATLAB or Scilab to transform a continuous state space into discrete state space, and then you simulate the system, and the sample time is 0.01 seconds, and the input, okay, let me give the input as well, and the input of the system is impulse, okay, unit pulse. So let me add more. If and the input is unit pulse. Okay, so now you try by yourself. I won't show any hint, but you can ask and I will answer accordingly.